Welcome to the presentation on search algorithms in artificial intelligence. Let's recap the search algorithm terminologies. Searching is a step-by-step procedure to solve a search problem in a given search space. Search space represents a set of possible solutions, which a system may have. Start state. It is a state where the agent begins the search. Goal test. It is a function which observes the current state and returns whether the goal state is achieved or not. Search tree. A tree representation of search problem is called search tree. The root of the search tree is the root node which is corresponding to the initial state. Actions. It gives the description of all the available actions to the agent. Transition model. A description of what each action do can be represented as a transition model. Path cost. It is a function that assigns a numeric cost to each path. Solution. It is an action sequence that leads from the start node to the goal node. Optimal solution. If a solution has the lowest cost of all solutions. The properties of search algorithms are: completeness. A search algorithm is said to be complete if it guarantees to return a solution if at least any solution exists for any random input. Optimality. If a solution found for an algorithm is guaranteed to be the best solution, lowest path cost, among all other solutions, then such a solution is said to be an optimal solution. Time complexity. Time complexity is a measure of time for an algorithm to complete its task. Space complexity. It is the maximum storage space required at any point during the search, as the complexity of the problem. There are two types of search algorithms. One is uninformed search or blind search. Second, informed search or heuristic search. Informed search algorithms use domain knowledge. In an informed search, problem information is available which can guide the search. Heuristic means additional information. Consider a case of searching for a house. The address is the source and we use that in uninformed search. But we got a clue like it is a pink-colored double-story building. The search makes easy. That clue is heuristic information. A heuristic is a way that might not always be guaranteed for the best solutions but guaranteed to find a good solution in a reasonable time. An example of informed search algorithms is a traveling salesman problem. Greedy search. A search. Etc. An uninformed search is a class of general-purpose search algorithms that operates in brute force way. Uninformed search algorithms do not have additional information about state or search space other than how to traverse the tree, so it is also called blind search. Following are the various types of uninformed search algorithms. Breadth-first search. Depth-first search. Depth-limited search. Iterative deepening depth-first search. Uniform cost search. Bidirectional search. Breadth-first search is the most common search strategy for traversing a tree or graph. This algorithm searches breadth-wise in a tree or graph, so it is called the breadth-first search. BFS algorithm starts searching from the root node of the tree and expands all successor nodes at the current level before moving to nodes of the next level. The breadth-first search algorithm is an example of a general graph search algorithm. Breadth-first search implemented using the FIFO-Q data structure. Advantages. BFS will provide a solution if any solution exists. If there is more than one solution for a given problem, then BFS will provide the minimal solution which requires the least number of steps. Disadvantages. It requires lots of memory since each level of the tree must be saved into memory to expand the next level. BFS needs lots of time if the solution is far away from the root node. Consider the tree structure. We have shown the traversing of the tree using the BFS algorithm from the root node S to goal node K. BFS search algorithm traverse in layers, so it will follow the path which is shown by the dotted arrow, and the traversed path will be we start the root node S and goes to nodes A, B, C, D, G, H, E, F, I, and finally the goal node K. BFS algorithm. Set a variable node to the initial state, that is, the root node. Set a variable goal which contains the value of the goal state. Loop each node by traversing level by level until the goal state is not found. While performing the looping, Start removing the elements from the queue in FIFO order. If the goal state is found, return goal state, otherwise continue the search. The performance measure of BFS is as follows. Time complexity of the BFS algorithm can be obtained by the number of nodes traversed in BFS until the shallowest node, where the D equals depth of shallowest solution and B is a node at every state is big O of B raised D. The space complexity of the BFS algorithm is given by the memory size of the frontier, which is big O of B raised D. BFS is complete, which means if the shallowest goal node is at some finite depth, then BFS will find a solution. BFS is optimal if path cost is a non-decreasing function of the depth of the node. Uniform cost search is a searching algorithm used for traversing a weighted tree or graph. The primary goal of the uniform cost search is to find a path to the goal node which has the lowest cumulative cost. Uniform cost search expands nodes according to their path costs from the root node. It can be used to solve any graph or tree where the optimal cost is in demand. A uniform cost search algorithm is implemented by the priority queue. It gives maximum priority to the lowest cumulative cost. Uniform cost search is equivalent to the BFS algorithm if the path cost of all edges is the same. The advantage is uniform cost search is optimal because at every state the path with the least cost is chosen. The drawback is it does not care about the number of steps involved in searching and only concerned about path costs, due to which this algorithm may be stuck in an infinite loop. In the search tree, it is seen that the goal state is G and start or initial state is S. There are 3 paths available to reach the goal node. We need to select an optimal path that may give the lowest total cost. Therefore, the path is S, A, D, G gives the optimal path cost is 1 plus 2 plus 3 equals 6. Uniform cost search algorithm. Set a variable node to the initial state, i.e., the root node, and expand it. After expanding the root node, select one node having the lowest path cost and expand it further. Remember, the selection of the node should give an optimal path cost. If the goal node is searched with optimal value, return goal state, else carry on the search. The performance measure of uniform cost search. Uniform cost search is complete, such as if there is a solution, UCS will find it. Let C is cost of the optimal solution, and epsilon is each step to get closer to the goal node. Then the number of steps is equal C by epsilon plus 1. Here we have taken plus 1, as we start from state 0 and then to C by epsilon. Hence, the worst case time complexity of the uniform cost search is big O of B raised 1 plus C by epsilon slash. The same logic is for space complexity, so the worst case space complexity of uniform cost search is big O of B raised 1 plus C by epsilon slash. Uniform cost search is always optimal as it only selects a path with the lowest path cost. The depth-first search strategy explores the deepest node first, then backtracks to explore other nodes. The depth-first search is a recursive algorithm for traversing a tree or graph data structure. It is called the depth-first search because it starts from the root node and follows each path to its greatest depth node before moving to the next path. DFS uses a stack data structure for its implementation. The advantage of DFS is, DFS requires very little memory as it only needs to store a stack of the nodes on the path from the root node to the current node. It takes less time to reach the goal node than the BFS algorithm. The disadvantage are: there is the possibility that many states keep reoccurring, and there is no guarantee of finding the solution. DFS algorithm goes for deep down searching and sometime it may go to the infinite loop. In the search tree, we have shown the flow of depth-first search, and it will follow the order as the root node, left node and right node. It will start searching from root node S, and traverse A, then B, then D and E. After traversing E, it will backtrack the tree as E has no other successor and still goal node is not found. After backtracking it will traverse node C and then G, and here it will terminate as it found goal node. DFS algorithm. Set a variable node to the initial state, that is, the root node. Set a variable goal which contains the value of the goal state. Loop each node by traversing deeply in one direction or path in search of the goal node. While performing the looping, Start removing the elements from the stack in the LIFO order. If the goal state is found, return goal state, otherwise backtrack to expand nodes in other direction. DFS search algorithm is complete within finite state space as it will expand every node within a limited search tree. The time complexity of DFS will be equivalent to the node traversed by the algorithm. It is given by Tn equals 1 plus n raised 2 plus n raised 3 plus etc. plus n raised m equal to big O of n raised m, where m equals maximum depth of any node and this can be much larger than d, shallowest solution depth. Space complexity of DFS algorithm needs to store only a single path from the root node, hence space complexity of DFS is equivalent to the size of the fringe set, which is big O of b raised m. DFS search algorithm is non-optimal, as it may generate a large number of steps or high cost to reach to the goal node. A depth-limited search algorithm is similar to a depth-first search with a predetermined limit. Depth-limited search can solve the drawback of the infinite path in the depth-first search. In this algorithm, the node at the depth limit will treat as it has no successor nodes further. Depth-limited search can be terminated with two conditions of failure. Standard failure value, it indicates that the problem does not have any solution. Cutoff failure value, it defines no solution for the problem within a given depth limit. Advantages are: depth-limited search is memory efficient. Disadvantages are: depth-limited search also has a disadvantage of incompleteness. It may not be optimal if the problem has more than one solution. In the search tree, let the depth limit is 2, that is level 2. So, only levels 0, 1 and 2 get expanded, starting from the root node S, till node C. It is not giving a satisfactory result because we could not reach the goal node J. So it moves to B and then I and finally the goal node J. So the path is S, A, C, D, B, I, J. Depth-limited search algorithm. Set a variable node to the initial state, that is, the root node. Set a variable goal which contains the value of the goal state. Set a variable limit which carries a depth limit value. Loop each node by traversing in the DFS manner till the depth limit value. While performing the looping, start removing the elements from the stack in LIFO order. If the goal state is found, return goal state. Else terminate the search. The performance measure of depth-limited search are: DLS search algorithm is complete if the solution is above the depth limit. The time complexity of the DLS algorithm is big O of b raised L. The space complexity of DLS algorithm is big O of b into L. Depth-limited search can be viewed as a special case of DFS, and it is also not optimal even if L greater than D. The iterative deepening algorithm is a combination of DFS and BFS algorithms. This search algorithm finds out the best depth limit and does it by gradually increasing the limit until a goal is found. This algorithm performs a depth-first search up to a certain depth limit, and it keeps increasing the depth limit after each iteration until the goal node is found. This search algorithm combines the benefits of the breadth-first search's fast search and depth-first search's memory efficiency. The iterative search algorithm is a useful uninformed search when search space is large, and the depth of the goal node is unknown. The main advantage is: it binds the benefits of the BFS and DFS search algorithms in terms of fast search and memory efficiency. The main drawback of IDDFS is that it repeats all the work of the previous phase. The drawback of iterative deepening search is that it seems wasteful because it generates states multiple times. The tree structure is showing the iterative deepening depth-first search. The iterative deepening depth-first search algorithm performs various iterations until it does not find the goal node. The iteration performed by the algorithm is: first iteration, it visits only A. Second iteration, visits the nodes A, B, C. Third iteration visits nodes A, B, D, E, C, F, G. Fourth iteration visits the node B, D, H, I, E, C, F, K, G. In the third iteration, the algorithm will find the goal node .G and terminates .A. Iterative deepening search algorithm. Explore the nodes in DFS order. Set a limit variable with a limit value. Loop each node up to the limit value and further increase the limit value accordingly. terminate the search when the goal state is found. The performance measure of iterative deepening depth-first search. This algorithm is complete if the branching factor is finite. Let's suppose B is the branching factor and depth is D, then the worst case time complexity is big O of B raised D. The space complexity of iterative deepening depth-first search will be big O of B into D. Iterative deepening depth-first search algorithm is optimal if path cost is a non-decreasing function of the depth of the node. The bidirectional search algorithm runs two simultaneous searches, one from initial state called as forward search and other from goal node called as backward search, to find the goal node. Bidirectional search replaces one single search graph with two small subgraphs in which one starts the search from an initial vertex and other starts from goal vertex. The search stops when these two graphs intersect each other. Bidirectional search can use search techniques such as BFS, DFS, DLS, etc. Advantages are: bidirectional search is fast. Bidirectional search requires less memory. The drawbacks are: implementation of the bidirectional search tree is difficult. In a bidirectional search, one should know the goal state in advance. In the search tree, the bidirectional search algorithm is applied. This algorithm divides one graph or tree into two subgraphs. It starts traversing from node 1 in the forward direction, and starts from goal node 16 in the backward direction. That is node 1, node 4, node 8, node 9, etc. in the forward direction and node 16, node 12, node 10, node 9, etc. in the backward direction. The algorithm terminates at node 9 where two searches meet. The performance measure of bidirectional search. Bidirectional search is complete if we use BFS in both searches. The time complexity of bidirectional search using BFS is big O of B raised D. The space complexity of the bidirectional search is big O of B raised D. The bidirectional search is optimal. The comparison of 6 search algorithm is given in the table.
Thank you, and have a nice day.